Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video, of course. And today's lesson topic is all about special right triangles. This will be the part one. I'll have two parts made for this lesson because I don't want to confuse you. I want to separate these fundamentals from these more advanced topics. Of course, that's how we roll here at eCoreAcademy. We're trying to get those fundamentals so that later on we can hypertensively focus on those enrichment topics, those that you might not necessarily see in your basic classes, but maybe your higher level classes, maybe in the SATs, and maybe in your final exams at the end of the year. So it's very important that we address the fundamentals before we get into the high level concepts. So before we jump into the meat of today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications so you don't miss out on any of our latest uploads and that you'll stay up to date. Also, feel free to utilize the comment section down below. Leave down there any of your comments that you want us to hear out, such as constructive feedback, or if you just want to ask us any questions. Of course, I'll have the email up in the description down below, as well as on the last slide. So don't worry if you want to communicate with us, but we will try and implement all of your comments and your constructive feedback in all of our videos to come. So all four of those things are very greatly appreciated. As I was saying, our lesson focus, hypertensively, our goal for today's lesson is to discover what the properties of special right triangles are and how exactly they can apply to the law of sines and cosines. So we're going to identify what these special right triangles are, of course, their underlying properties, what make them special, and how they can correlate to other oblique triangles, in essence, to apply to the law of cosines and the law of sines. So this is a good transitioning in between our law of sines and cosines into our special right triangles, because we're going to utilize them, building off of these fundamental topics and leveraging them as we go into these later topics in our course. So let's jump right into it. So before I jump into the meat of our lesson, and before I jump into like the basic concepts, I just want you to ask yourself a question. When you hear this topic, special right triangles, of course there's something unique about them, and I want you to ask yourself this question: is there a smooth formula for area? Now, what exactly do I mean by that? When it comes to the area of a triangle, it applies to all types of triangles. That's base times height over 2. But it can only be represented by right triangles. And what that means is if you're given an oblique triangle, which is any triangle that's not a right triangle, you cannot smoothly calculate the area out. You have to be given an extension of an altitude. Your base is already going to be created, but you have to be given an extension of an altitude. However, with a right triangle, you're automatically given that altitude as one of the side lengths in your right triangle. And also, it's derived directly from a square or a rectangle. So that right triangle is derived, area triangles are entirely derived from that of a rectangle. And a right triangle is an accurate representation of that, but oblique triangles do not have that property. But how exactly can we correlate that? Can we find right triangles in oblique triangles and utilize their properties to easily calculate their areas without having to be given that extra altitude, which is basically a give me? It's not how it works out here in the extra geometric concepts that are much more higher level, much more complex. At the beginning, you were thinking, oh, you have to be given this amount of measurements, these amount of measurements. Well, no, you have ratios that are available, and these ratios come very handy when it comes to your higher level math courses. It's a great lesson here. This whole unit is very important and something that's not often covered in geometry. So please make sure to pay attention, as you'll be most likely utilizing this in AP final exams and of course the SAT as well, and competition math. So if we look at our diagram right here, as you can see, we have two different oblique triangles. And what we're basically doing is we're identifying right triangles that are located within these oblique triangles, or we can develop right triangles utilizing at least two of these measurements as shown here. And with right triangles, you get that easy ticket to your area formula. And if you look closely at both of these triangles here as shown, you can see that our altitude is being represented here. And that's very important part. The altitude is what gives your right triangle its value, because the altitude is one of the side lengths of your right triangles. So if you want to correlate this with one of your oblique triangles as shown here, you're going to want to find the altitude and make that one of your legs of your right triangle. And I'll show you in our next video, part 2, how exactly that comes in handy and what the reasoning is for that, the origins of that method. So let's move on. Let's look at special right triangles part 1, what you guys came here for. So let's look at deriving special right triangles. Let's look at exactly how these are derived, and then I'll go through the breakdown definitions of what exactly they are and possess, and how they apply to the law of cosines and sines. So the square root, just before, like a reminder before we jump into these equations, I just want to remind you of these whole square root radicals, what they actually are, radicands and radicals, what they actually are. And all it is in this situation, what we're going to come across is that you have to know that the square root of a number is the two numbers multiplied by themselves that equal the number. So if we're given, 25 is our number, 25 equals 5 times 5, which equals 25. Or if you're looking at it in a radical expression, square root of 5, or root 5, times root 5 is equivalent to root 5 squared, which is merely equal to 5 because that square cancels out your radicand. It's basically your opposite function of an exponent. And right triangles with measures 45, 45, 90, and 30, 60, 90 are special right triangles, as shown here. So these are two special types of right triangles that we're going to be focusing on in this trigonometry unit. There's a third one, but I will refer to that at the end of this unit. But these are the two main focuses. So two main focus. Two triangles of focus. They're not intercorrelated as much as you'd think. Right triangles themselves are already intercorrelated. I'll be showing you that on the next slide through similarity. But these are not. They don't possess unique properties that are only consistent amongst each other. But if we're looking at these, but of course, other than the fact that they're special, meaning they're unique and they're much smoother with these area formulas. So if you look here at 45, 45, 90, what that's basically saying is it's identifying all of your angle measures, meaning it's representative of all those angle measures. And since we know it's a right triangle, there's not much altercation that you need. Your hypotenuse is always going to be worth your a squared plus b squared equals c squared. Your Pythagorean theorem is always going to apply. So it's only going to be identified by your angles. And of course, your 90 is going to be consistent as shown here. And then just those two acute angles are going to be different. And if you're looking at this 45, 45, 90, what you can automatically see is that your two side lengths that are not the hypotenuse, so this is your hypotenuse, the two legs of your right triangle, which is the two sides that are not the hypotenuse, are both going to be equivalent. They're both going to equal each other. They're going to be equivalent. And then your hypotenuse is going to be root 2 times your given x legs. And of course, that's because of the fact that you have these two angles here, and those two angles make this an isosceles right triangle in which two angles and two sides will be equivalent. If we take a look here at this 30, 60, 90 triangle, we have this correlation in between 30, 60, 90 multiples of 3, meaning you're multiplying the multiples of 30, and you're multiplying by 2 each angle that you go. So you're going to have a corresponding increase in size. So you have your x here as your base, your shortest side here. And then this is going to be worth root 3x. And then the hypotenuse is worth 2 times that value of x. Special right triangles part 2. Let's look at deriving special right triangles continued. So the diagonals of a square are what form the 45, 45, 90. Remember, triangles are going to be derived from your area formula. They're going to be identified by the area formula, just as any other figure. And these triangles are actually going to be derived from your given rectangles and your squares. Now, 45, 45, 90, keep in mind, like I said, it's an isosceles right triangle. That means since 2 of its angles are going to be equivalent, 45 and 45, that means 2 of its sides are going to be equivalent. And when you have 2 legs that are equivalent, that's going to be 1/2 of a square. And that's exactly where this formula has been derived from. So we take a look, if I draw out this square here, and we divide this by half. This is one diagonal. If we just take a look at one diagonal here, we have two 45, 45, 90 degree triangles formed. But when I split it like this, you have your 4 equilateral triangles formed. And I'll explain to you what that is, but we're only going to take a look. I'll explain to you what that is in the next video. But if we just take a look at this one diagonal that comes across, it's going to connect opposite vertices together. If we look at that, we'll just put these vertices of these sides of points of focus. If we look at this, we have a right angles, because remember, the angles that are not broken up in a square are always going to be 90 degrees. So this is going to be 90 degrees. But then we look over here. This 90-degree angle has been split into two. That's what a diagonal does to a square. It always splits it into two, bisects it. So that means this is going to be 45. This is going to be 45. This guy is going to be 45. And this guy is going to be 45. And that's where this whole equation is being derived from. Well, the equation we haven't necessarily gotten to yet, but this is where this whole property is being derived from, the properties of the triangle. And of course, I'll get into the formulas and more complex equations in our next video, part 2. So the altitude and area of an equilateral triangle is determined by the 30, 60, 90 triangles. So if you take a look at 30, 60, 90, you're like, well, how does that come into play? 45, 45, 90 triangles. Well, they actually have correlation. They have two equivalent sides, which we know in this day and age. If you're given one measurement, you can complete the entire triangle. And that's very important. However, 30, 60, 90, you're wondering, where is this derived from? Because deriving an equation or a given value is very important. It's just as important as the validity of it. Deriving it is your reasoning, and then validity is your proof. Two things that combine together and are representative of basically geometry. So if we take a look at an equilateral triangle here, oops, sorry about that. Try and make this as wide as possible so that you can see. So this is going to be an equilateral triangle. Which means it's also equal angular. So these angles are going to be equivalent. We'll put these vertices here. So all you're doing here is, if you're given an equilateral triangle, well, you're thinking to yourself, wow, equilateral triangles have really smooth postulates and theorems, and they have equal sides and equal angles. Why can't we just smoothly calculate the area? Well, it does not have a representative length or a side length that is representative of its altitude, which is necessary in a triangle. However, we can create that by 30, 60, 90 triangles. So all we do is we take that top vertex and we're just going to split and bisect the bottom side of this given triangle as shown. So I'm going to bisect it as shown here. And when you bisect, it's going to split into two different 90-degree angles. And these angles shown here. This guy is, if you think about it, an equilateral triangle is going to have three 60-degree angles. Always. That's always going to be the case. But if you think about it, if this is bisecting this whole side, this base of this triangle, and is making it to two 90-degree angles, that means you're also going to be bisecting this top vertex 60 into two different angles, which are going to be 30 degrees and 30 degrees. And of course, your 60 degrees are going to stay the same for these two sides. So that's how we derive our given 30, 60, 90 right triangle from an equilateral triangle. And this will come in handy when you're trying to calculate your given area of your equilateral triangle. You can find the area of 130, 60, 90 triangle utilizing our relationships and of course our later theorems in order to and then multiply by 2 to get the combined area of the entire equilateral triangle. Special right triangles, part 3, similarity and definitions. So all isosceles right triangles, which are triangles that have two sides that are of the same length, all isosceles right triangles are similar by the angle postulate, meaning if you have two angles that are automatically equivalent, that means you are, because all right triangles have 90 degrees, they're going to have 90-degree angles that are going to be equivalent as well. And then you just need one other angle in that given triangle to have three angles that are congruent. So if, say, for example, 45, 45, 90, if you have a 90-degree angle and a 45-degree angle representative of both triangles, that means they're both going to have the same interior angle measures, which would make them similar. That's the only thing identifying them. And then, of course, that automatically infers they have proportional sides. So let's look at our definitions. So 45, 45, 90 is an isosceles right triangle with interior angle measures of 45, 45, and 90. And the hypotenuse is root 2 times as long as either leg. So let's draw that out here. So if we take a look here at this right triangle here, this is going to be our 45, 45, 90. So this is going to be our 90-degree angle, obviously. This is going to be our 45-degree angle. And then this is going to be our other 45-degree angle. And when we're given these measurements, of course, we're going to try and look for ratios of side lengths now. So we know that this is isosceles, so two legs are going to be of the same length. So that means this leg here is going to be worth x, and this leg here is going to be worth x. And since they're both equivalent, we can put hypotenuse in terms of either one of the legs. So the hypotenuse is worth root 2 x, root 2 times x of each leg. So say, for example, you were given that x equals 4, and you want to discover what the radical form of your hypotenuse is. All your hypotenuse is going to equal is 4 times root 2. That's all it is, and then you can multiply that out. So it's 4 multiplied by root 2. Special right triangles, part 4. Let's look at similarity and definitions and the 30, 60, 90 triangle. So 30, 60, 90 triangle is a triangle with angle measures of 30, 60, and 90. And in a 30, 60, 90 triangle, the hypotenuse is twice the shorter leg and is root 3 the other shorter leg. So if we're going to draw that out here, I'm just going to refer to it in its organic form as a right triangle. So this is going to be our 90-degree angle, of course. And this is going to be our 60-degree. Let's make this our 30-degree angle here, because that matches with how I represented the top vertex being split in an equilateral triangle. So this is our 60-degree angle opposing to our 30-degree angle. And what are the relationships between the legs? So all we're referring to is the hypotenuse is twice the shorter leg. So if we're given our shorter leg here, this would be our shorter leg up here, x. That means that our hypotenuse here would be worth 2 times our x, so it's going to be 2x. And then our shorter leg is actually going to be worth root 3 times x, our other shorter leg. So that's the ratio here. So if we're given, a value of 1, x equals 1, that means that we have a root 3 times x, so it would equal root 3 for our bottom side here. X equals 1 here. And then for our 2x, it's going to be 2 times root 3. Just leaving these unsimplified. It's actually easier to leave these radicals unsimplified because you're most likely going to plug in other values if you're going to correlate it with our cosine and sines. But if you want to, you can just go ahead and simplify that. All right, so let's move on. Now, finally, let's look at these sines and cosines, and let's look at how 90-degree angles and specifically how special right triangles can apply in relationships between these two laws. So, we're just going to refer to the basic functions for today, but I will correlate with the laws tomorrow, in our next video when that comes out for part 2. So sine A equals cosine of B, and you're thinking, wait, what? How that doesn't really make sense to me. So this is what it means. So all it means is that if you're given your C angle, if we're referring to the triangle in forms of ABC, C being the 90-degree angle, ignore the side lengths for now. We have our 90-degree angle over here at angle C. Now, when it comes to a trigonometric function, remember, everything is in terms of your acute angle. Nothing is in terms of your 90-degree angle. That's very important to know. So that means that A and B in this circumstance are going to be the angles of focus, the possible angles of focus. These angles must add to 90. A plus B must equal 90. Because of the fact that you have 90 degrees as your automatic 90-degree angle, and all angles on the interior of a triangle, any type of triangle, have to add up to 180 degrees. So that means A plus B must be equivalent to 90. So if you think about it, if you're given, the fact in terms of A, if you're given, say, for example, 60 degrees in this case, and you calculate the sine of 60, okay? Now, what you have left here is 30 degrees, because this is a 30, 60, 90 that I've put up here. So what if you calculate the cosine of that given 30 degrees? The cool thing about these functions is that they actually are very highly correlated. So that means the sine of 60 is actually going to equal the cosine of 30. And how that works out is, I'll show you how that actually works out. Let me switch to my calculator real quick. Switch over the calculator. So we're looking at this calculator here, right? And I said sine of 60, correct? So we have sine of 60. and that equals 0.866. We'll round that off at 0.866. Now, if I calculate the cosine of 30, 60 plus 30 equals 90, so it has to be 30, or 90 minus 60 equals 30. So we have 60 and 30 here. And you can see that that will actually equal 0.866025, so it's the same exact value, and that's the equivalence that we're looking for right here. This equivalence here is shown. So with that being said, our sine of 60 and cosine of 30 are approximately 0.866, and they are actually equivalent, and that's represented by this here. So sine of A is equivalent to 90 minus cosine of 90 minus A, and the cosine of A is equivalent to 90 minus A times the sine function. All right, everyone. So that'll be it for today's video. This has been the eCoreAcademy e-learning platform today. Please make sure to like and subscribe down below. And don't forget to click that post notification bell so you don't miss out on any of our channels that it just uploads. And feel free to utilize that comment section down below. Try and check out our website at www.eCoreAcademy. All you have to do is make an account for free, and you get full unlocked access to what we as an online e-learning platform actually offer to you. We have integrated note sheets, quizzes, and worksheets to go along each and every single one of our videos, organized into their own separate lessons. Also, feel free to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. And finally, check out all of our socials in the description box down below. Full link is there for access at Facebook, Twitter, and Instagram. See what kind of interesting content we have there and use those mediums to share all of our videos. Once again, everyone, that'll be it for today's video. I hope you guys enjoyed. This has been AJ, and I will see you guys in the next one. Peace.